Okay, so this is the second part of the lecture. In the first part, we went through the basic ideas of GFS or HDFS. Now we will be back to MapReduce, and more specifically, we will be back to Hadoop. So Hadoop 101, this is the part of the lecture. So before we go through some details about Hadoop, I want to show you two small videos. Here is one about what is the origin of Hadoop, and the second is about the name of Hadoop. This one.
So let me tell you how Hadoop came to be. About 10 years ago, in around 2003, I was working on an open source. So let me tell you how Hadoop came to be. About 10 years ago, in around 2003, I was working on an open source web search engine called Nutch. And we knew it needed to be something very scalable because the web was, billions of pages, terabytes, petabytes of data that we needed to be able to process. And we set about, doing the best job we could. And it was tough. We got things up and running on 4 or 5 machines, not very well. And around that time, Google published some papers about how they were doing things internally. Published a paper about their distributed file system, TFS, and about their processing framework, MapReduce. So my partner and I, at the time in this project, Mike Caffarella, set about trying to re-implement these in open source so that more people could use them than just folks at Google. Took us a couple years, and we had Nutch up and running on, instead of 4 or 5 machines, on 20 to 40 machines. It wasn't perfect. It wasn't totally reliable, but it worked. And we realized that to get it to the point where it would scale to thousands of machines and be as bulletproof as it needed to be would take more than just the 2 of us working part-time. Around that time, Yahoo approached me and said they were interested in investing in this. So I went to work for Yahoo in January of 2006. First thing I did there was we took the parts of Nutch that were a distributed computing platform and put them into a separate project, a new project christened Hadoop. Over the next couple of years, with Yahoo's help and the help of others, we took Hadoop and really got it to the point where it did scale to petabytes and running on thousands of processors and doing so quite reliably. It spread to lots of companies, mostly in the internet sector, and became quite a success. After that, we started to see a bunch of other projects grow up around it. And Hadoop's grown to be the kernel of what's pretty much an operating system for big data. We've got tools that allow you to more easily do MapReduce programming. So you can develop using SQL or a data flow language called Pig. And we've also got the beginnings of higher level tools. We've got interactive SQL with Impala. We've got search. And so we're really seeing this develop to being a general purpose platform for data processing that scales much better and that is much more flexible than anything else that's out there. So the name Hadoop comes from my son's toy elephant. So the name Hadoop comes from my son's toy elephant. When he was about 2, a friend gave him a little stuffed elephant, which he played with incessantly. and we overheard him calling it something, this strange word that he invented, and said Hadoop. So I immediately wrote it down because I was in the software business and we're always looking for good names, and this one came with a mascot even. And a few years later, when I needed a project name, pulled it out. Now I wrote it down as Hadoop and figured that everyone would say Hadoop. Now it turns out everyone says Hadoop instead, but I persist in saying Hadoop. Now my son, of course, is 13 and expects royalties for the name. He wants more credit. He also accuses me of stealing the toy. At some point, he was using it in some kind of rocket ship experiment, and I had to rescue it, and now it lives in my sock drawer for safety.
Okay. So we are not alone to pronounce it that way. Okay, so let's talk about now the details of Hadoop API. Remember that we are implementing MapReduce, right? So there must be an interface to do the mapping and another interface to do the reduce phase, okay? So you will see in the documentation of Hadoop, there are two main classes, of course, among so many other classes, but these are the two main classes. The one that is called mapper, and the other is called reducer. And to write any MapReduce job, you will have to extend these two classes. The first class, which is the mapper, will have the function that will process the input of the job through the map function. So the map function is the map function that we talked about in MapReduce. So it takes one key value pair, okay, and it also takes the configuration of the job, because there might be some parameters that we need, that the user has to pass, and produce the output out of this pair of key and values. So that's the main function of that class. So this will be called once per key value pair in the input split. Now remember that one input split will be assigned to one mapper object, which means that the map function within that mapper object will be called once for every record, for every key value pair. Okay? Now there are two other supporting functions. The first one is called setup, and it will be called only at the beginning of the task. Remember, in the Hadoop terminology, the mapper called map task. Okay, so the task is processing an entire input split, a list of records. Okay, so at the beginning, before you process any record in the input split, the setup function will be called. It's up to the programmer to do whatever he wants to do some initialization before going through all the records of the split. And at the end, there is a function called cleanup that will be also called once at the end of the task, after processing all the records in the input split. Okay? So it is that simple. Of course, setup and cleanup, you don't have, it's up to you to do anything in them or not, but the main work will be done in the map function. Okay? So that's the mapper. The reducer and the combiner will have very similar API, except that this function is called reduce, and the input here is a bit different than the input, or the parameters here are different from the parameters of the map function. Okay, can you explain why the signature here is a bit different? We have just one key and many values. Yes. So the iterable here, the iterable interface is the object that will go through the values one by one, or by which you will actually go through the values one by one. Okay. So if you remember, at the beginning of the reduce function, you will have one key and many values that were associated with that key from the map phase. So every call to the reduce function will handle one key only, and of course a list of values. Similarly, there is a setup function that will be called at the beginning, and the cleanup function that will be called at the end. This is the basic Hadoop API or MapReduce API. Combiner is similar to the reducer. It takes a key and some values, right, and produce a key and value, or a list of keys and values. But the only thing is that the types have to be matching the output types of the mapper. And the output of the combiner has to be in the same types, exactly the same types of the output of the mapper. Reducers, of course, don't have to stick to that. Any questions about this API? Okay. Still one, which is the partitioner. Remember the two major components, map and reduce. There are two optional components, the combine and partition. The combine is done in the previous slide. The partition here is just a function within a class called partitioner. You will overwrite it, and it will take a key and value and return back a number that will indicate which reducer will handle that record. Okay, and you don't have to implement that. Of course, by default there is one already that can be used for you. But as you will inshallah see, maybe next lecture or the lecture after, we will use this in one of the design patterns of MapReduce to do some efficiency tricks that we'll inshallah study. But for now, it is optional, and it depends on what the actual application that you are doing. Questions? Now, of course, there is the configuration of the job. You need to specify the input and the output paths. You need to specify the input and output formats. You need, in that configuration, you need to specify where is the mapper class, where is the reducer class, combiner, partitioner classes. You need to also to specify the types of the intermediate output, which is the output of the mapper. And you need to also specify, you don't have to, okay, I think you have to, but there is a default, I think. Not very sure of that. But you can specify the number of reducers, okay, but you cannot specify the number of mappers. You can give a hint, but the number of mappers actually will depend on the size of the data. Okay? And don't always depend on the defaults. You have to understand what are the defaults are, because they might not work well for your purpose. Okay? Okay, now let's talk a bit about some of the data types. There is a data type called writable. Every key and value in Hadoop has to implement writable. Okay, it has to implement that interface. That interface will define how the data is serialized and how the data is deserialized, how the data is read and how the data will be written. Okay, so it has to be of that type. All the input and the output has to be of that type. There is a type that extends that, which is called writable comparable, and you use that when you want to sort. You want the data to be sorted. Which part of the data types has to be sorted in the MapReduce job? Keys. There are multiple keys. There is an input key, there is an output key from the map function, there is input key to the reducer, and there is output key of the reducer. Which key you mean? Because these can be different types, right? Not all of them have to be sorted. Let's take them one by one. How about the input key? Would that have to be sorted? No, we don't have to sort it. How about the output of the map phase? Yes, it has to be sorted because that is essential for grouping. So I have to know how to compare between two values of that key, of that type. So it has to be comparable. Okay? With me? Okay. How about the output? How about the input to the reduce function?
It's already sorted.
Why? No. Okay. Let me ask it in a different way. Remember the data type of the output of the map function? We have key and value here, right? And the reduce also has input, which is key and value also, key and list of values. What is the relationship between the type of the key in the intermediate output and the type of the key in the input of the reduce?
They must be the same.
They must be the same. Yes, they must be the same. Okay, so of course by default they are also comparable. Okay, is that clear? How about the output of the reduce function? Does it have to be sorted?
It might be, but it doesn't have to.
Yeah, it doesn't have to.
Yeah.
It doesn't have to. Okay? Doesn't have to. So the output type of the mapper is the one that has to implement this one. Okay? Other types they don't have to. Do you have a question, Ree? The others are not, yeah. But it's not a requirement here. There are already some implemented classes for you within Hadoop code, like int writable. So this is an integer that is writable. Long writable, this is the long type, but is writable. Text, which is the version of the string that is writable, and so on. So there are some types. You should look at them to know if some of them will be usable in your application or not. You don't have to implement from scratch. There are some that are implemented for you already. So these are concrete classes for different data types. There is also a type called sequence file, which is the binary version that will be the output, will be the type of the output. Okay, that's how the output will be written in a file. Okay, you can write in text files, by the way, but usually we write in sequence files because it's not always the case that you deal with text. Okay, so the sequence files is an encoded sequence of key and value pairs. You can use them for input, and also you can use them for output. Okay. They are not related to the size. They are related to how the data is encoded in the files, the input and output files. Okay.
It's faster to use sequence file than the file than
It is faster.
text.
It is faster, yes. Continuing in Hadoop. Now we'll look into the code, the actual code. Remember this slide from last time? Right? So that was the pseudocode for the Hello World MapReduce program, which is the word count. Okay, so we discussed about this in detail last time, but we didn't see the actual code. This is just pseudocode. Here is the actual code in Java. So you'll see that there is a mapper class. Okay. You have to extend the actual mapper. So this is my own class that extends the mapper. And you see here that the mapper has 4 parameters of types. What are these 4? Huh? Why do you have 4 types here?
Key, you have value, you have those are the types of the and value, right?
Yes, this is 2. What are the other 2?
Input output.
Input and output, yes. Okay, so we have key type, key input type, value output type, key input type, value input type. So these are for the input, key and value pairs, and these are for the output of the mapper, key and value pairs. Okay, like why do we have these like that? Long writable here because when you read text by default, you will get the offset as the key. Remember, word count was counting words in text, right? So by default, the key, when you read from textual files, the key will be the offset of the line. And the value will be 1 line. Of course, you can change that if you want, but that's the default. Okay, so the key will be the offset of that line within the file, which is not used here at all. We don't need it, and the text is 1 line. Okay, and it is text because it is text. It is string. Okay, remember everything has to be writable. So these have to be writable types. Okay, types that implement the writable interface. And how about the output? Why is it text? Yeah, remember we output the word and 1, right? So the output is the key is text and the value is integer. Okay. Remember, we cannot use int. We cannot use long. They have to be the writable versions of these data types. And the primitive data types, all of them, they have their corresponding writable types already implemented for you. So whenever you need something that is primitive, they are there. If you want, of course, something that is more complex, you can implement your own. Let me skip this for some time and we'll get back to them. Now let's look at the map function. The map function takes the key and value and it goes through the text. It uses a string tokenizer that will just produce the tokens, the words of the text, and going through them, for each one it will write 1 word and the output 1, which is indicating that it is 1. Okay. If you look at what is this word and this is what is that 1, you will see that they are static within the class. And we will say later, I think, that this is important to understand. You don't need, or you should try to avoid creation of objects as much as you can, which means that you need to, as much as you can, reuse objects. Okay? Because creation of objects takes a lot of time and memory. Okay? So you'll have to be very efficient in that. That's why we define them as static, so they will be defined once per object. And whenever the map function is called, they will be just reused. So you will see that this is actually constant, we will not change it, it's always 1. And this one, we will, every time we get a new word, we'll just set the word, the function set here is like assignment to that variable. So it will be assigned to the new token. Okay? And then we write this, the key and value. Any question about this? Are you with us? Any questions? Is that clear? Okay. Right. Then this is the reducer. Again, 4 types. 2 are the input and 2 are the output. And you notice, of course, that this has to be exactly these 2. The same type of the output of the mapper. Because the output of the mapper will go to eventually to the reducer. So they have to be of the same type. Okay? And this is, these don't have to be, of course, the same, but they happen to be the same here because eventually I want to say this word appeared that number of times. Okay, so the output will be text and integers. And the only difference here is that we go through the values through the iterable, so we'll use an iterator here. We get the iterator from here and we use it. I think you are familiar with iterators in Java, right? Okay, so iterator is an object that goes through the list of values one by one. So you use the function hasNext to check if you still have something that is not processed yet, and then get will give, and then next will give you the new value. Okay. Here, what we want to do is to count the number of times, right? So for all values, these are values produced by the mapper. We want to sum them, right? So we need to get the integer value from the values, sum them, and then write them out. So we need to get, so the function get, you will use it to get the actual value from the writable objects. Remember, every primitive data type has the corresponding writable object. Okay, so int has int writable. To get the actual integer value, you use the function get. Okay, and same for other writable types. Okay, so get here will give you, so iter.next will give you the int writable object, and then get will give you the integer value to sum it to add it to the current sum. Eventually, you need to produce the sum into a writable object. You cannot just say here sum. Okay, the write function produce one output record. So that's the key. The key is constant, right? It doesn't change. And you cannot just say sum here. Why is that?
Because it needs to be of type integer.
Yes, sum is just int, and you have to assign it to a writable version, which is int writable, which is the result. So you see
There are
here.
libraries that needs to be imported for this to be implemented.
The int writable is implemented already, yes.
What I'm saying, when we are building this, we should import the libraries that implement this.
Oh, of course, yes, this is Hadoop, yes.
Yeah.
You have to import all libraries in Hadoop, yes, of course. Yeah, I'm showing you that the code that you write, but that's not the whole Java file. Questions? I see silence, quiet. What does that mean? Okay, but it is very important to understand these things. I will share with you very nice and important tutorial that is given through Hadoop documentation, which shows you all of this code and explains it very well. Okay, I don't know if you got access to the documentation on Hadoop website or not. Did you try it? You will have to very soon. And this is the main function that that will submit the job. Okay, so you define a configuration variable which will have all the information about your job. You set the job and you set the classes. You say this is the main class, the class that has the main function. Okay, and this is the class of the mapper. This is the class of the combiner. This is the class of the reducer. You set the output key classes, also the types. You have to define the types in advance. And this is sometimes a source of errors. Sometimes you copy this code from one job to another, and you forget to change these types to align with the types in the classes. Okay, so be careful. Of course, you have to specify what is the input path and what is the output path. and those, by the way, have to be HDFS paths. Remember, the MapReduce job will read the input from HDFS and write the output in HDFS. So these paths have to be HDFS paths, not local paths. Okay? And this will just wait for the job until it completes.
The order is not out of control.
Sorry?
The
order of these? Ah, of course not. This is just adding some information to the configuration file or to configuration object. Okay?
The last one, what it does, wait for compilation.
This is just to say that I will submit the job and I will not return until it completes. Okay? I thought that you have a question. Do you have a question? I'm asking too much about whether you have questions more than your questions themselves today. I don't think it was the case last time. What's going on?
But there is nothing, at least for me, there is nothing unclear, but I think somebody said when we hit the real thing, there will be hundreds of questions.
Okay. 3 things to remember. As I said, avoid object creation if possible. This is a very critical point. I myself suffered from that, or I saw it. Okay, when you just create objects not in an efficient way, it will really slow down everything. So please try to avoid object creation, which means that you need to reuse objects as much as you can, instead of creating new objects, because you know in Java you cannot delete objects explicitly, so you'll have to wait until the garbage collection is done, and you never know when it will be done. It's a big overhead. Okay, so and remember, if for example, let's go back to this just to show you an example. What if I created that object within the reduce function? So it's not static. It's just I moved this line without the static part, just as a variable inside. It's not a member for a variable. It will be just a variable inside, and I create the object within that function. What will happen?
Every time
It will be created every call. Every call. What's the problem? It's just a call. This is millions of records will be called, okay? Which means millions of objects will be created unnecessarily. So it will consume memory, and also, of course, it will consume time. Time of creations and time of garbage collection. Okay? Okay. Another thing that you need to also understand, the execution framework uses value object in reducer. So if we go back here, don't store the values out of this, because the reducer reuses objects. It doesn't give you a new object every time. It reuses the same object but with a new value. Did you get that? Okay. Okay, now you see this object values. This is an iterable, right? So every time it will give you a value. Okay, this is an object, right? You get an object of that type every time you call the next function, right? Okay, don't think that these are different objects in the loop. Not every time you call .next, you'll get a new object You'll get the same object but has a new value. Okay? And let's say for example that the values here are 1, 5, 17, 3. We have only 4 values. Okay? So the first time that this function will be called, you will get an object of which is int writable that has an integer value that is 1. The next time you call next, you get the same object, but inside it there will be 5.
So what does it do? Does it reset between in each iteration?
Yes, every time it reuses the same object just to save time. The reducer does that automatically. It's not, you don't control it.
Set some value to it, or just, I mean, if it is the same object,
Yes,
object cannot
it's the
design,
same.
design
It's
without
okay.
it,
Okay. Okay.
right?
Just okay. Let me show that. Here's the memory. Okay, the memory has you have a variable in that memory. Okay, this variable called v. You create that object once. I'm now talking from the Hadoop point of view. Okay, you don't see that, but this is what happens when you call this function next the first time. This object will have the value 1 because we have 1 here. Okay, so v will be returned as the pointer of v, but the value inside the actual value inside it is 1. The next time you call next, you will get the same pointer v, but now this is not 1, this is 5 because we have 5 now. So it's the same object, but the value inside it changes over time.
I understood that. My question was just, does it reset when it goes to the new iteration, or it holds 1 until it gets the new value and overwrites it to 5?
No, whenever you call next, of course, it will be reset to the new one. Yani it's done here. It's done here. The new value will be set inside this next function.
Holds 1 until it next is called and
Yes.
overwrites to 5.
Yes.
That's what my question.
Yes. Now, what is the implication? You understood that now, right? Now, what is the implication of that? Why should we care about that?
We have only one option.
Okay, why should we care about that?
We are not using a lot of space by creating objects. And
Okay, thank you, Hadoop, that you are doing that. Why should we care about that?
Not to create many variables.
Thank you, Hadoop. Why should we care about that?
We shouldn't reset or change that variable inside. And this will overwrite until that we have.
We cannot because we get a copy of it. We get a copy of it. Okay, we cannot. I got your point. So you mean you can set something inside it. You can change the values of it, but doesn't matter because next time when you call next, you will get the new value anyway. The point here is that sometimes in some applications you might think that you want a copy of these values. You want to copy them in an array or to do something. Okay, so you tend to copy whatever you get from here into the array. Eventually, you will find all values will be equal to the last value because all of them are actually the same object. You are just getting copy of the same thing. You are getting copy of the same pointer.
That's why we are assigning this to the variable sum. So basically, you can operate with the sum rather than with the.
But here we don't need a copy of all values. We just aggregate them. But in other applications, you might need to get a copy of all of them because you want to do something with all of them at once. Okay? So in that case, you have to actual copy of the value, not just copy the pointer that you get, because the pointer points to the same object. If you do just copying of the pointer, eventually you will have an array of one value, copies of the last value at the end. Okay, so watch out for that. Is that clear? These small things are very important, and they are nice sources of bugs in your code. Passing parameters or data via class statics will not work. You should not pass parameters through the static primitives. You should pass the parameters through the configuration files, the configuration objects. You see it here? This is the object. There is a way to set parameters here. And this one is accessible through, where is the context? Through this, and in the mapper through this. So you can get all the parameters that you need. What if your job has a parameter value n? You need to do something with that parameter. You don't know n in advance, but it will be passed to you. Okay? Don't make it a static variable, because that is only local for one mapper. Okay? You need to get it through the configuration from the main function. You set it in the main function of the job that has this part. Okay, this configuration. There is a way to set parameters here, and you will get these parameters in the mappers and the reducers through the context variable. Okay. So that's again configuring the parameters directly in the job object.
So could you please go back to the previous slide?
Yes.
How the data is passed from the mapper to the reducer?
How?
Yes. Go back to the previous.
Go back to the code. Here?
We are first calling my mapper, yes?
Say it again, I don't hear you well. Can you...
Now the data, we have the input, the output of the mapper,
yes?
then the input, it comes from the mapper, yes?
Yes.
So this is the main program.
Okay, this is not the main program. This is setting up the job of MapReduce. It tells the runtime
This is
the configuration. These are the classes. But it doesn't run. Until this point, we didn't run anything. We didn't submit anything. Okay? Good point. Until calling this, we didn't do anything. Once we call this one, now we submitted the job to the cluster. And now the work will start. Okay? I finally get good questions. Or any questions at all. I'm worried. Okay. What is the issue of the side data? Sometimes in some jobs you want to read a table somewhere, from somewhere, okay, or a file, specific file that you want to read within each worker. Okay, maybe some dictionaries or something like that. You can do that in two ways. There is a mechanism in MapReduce called distributed cache. You set it within the job configuration here. There is a way to set the distributed cache. You say where exactly the files that you want to share. Because that, if you specify that, then this will be shared to all workers. Whenever a worker is assigned that job, it will have access to that file. Okay? So that's one way. The other way is to read directly from HDFS in the setup method. Remember the setup method? The setup method is called once before you start your processing. So within the setup method, you can read data from HDFS. Right? You can read that data, load it in memory, do whatever you like with it. You can also write side data in the cleanup function if you want. If there's some information that you want to write directly to HDFS, you can through the cleanup function. So the setup function and the cleanup function are hooks in the API that will allow you to deal directly with the distributed file system whenever you read or write to it. But that has nothing to do with the process of MapReduce. The process of MapReduce will depend on the records that you will write using the write function. Using the write function here. This is what will be grouped, not what you will write in the cleanup function or in the setup function. That's why we call them side data. These are not the main data. Whether you read it or write it, this is side data. It's dependent on what you are doing. But what will be grouped in the shuffling phase is what is written through this function. And the actual output of MapReduce will be also depending on this function, the call of this function. Okay? We mentioned that there are corresponding writable types of the primitive data types. You can, of course, also define complex data types. Now, there are two, at least, ways of doing that. The easiest way is to encode them as text. And convert, what do you mean by complex data type? It's a structure of different data types, right? Maybe integer and string. You want to put them as a value. Remember that you have key and value at the end, right? So if you want to produce multiple things, you have to combine them in a complex data type. So one way, which is easy in terms of programming, to convert them into text and encode them somehow. So if you want to produce A and B, you can encode them that way. Maybe separate them by column. You concatenate them, exactly. And then to read them, you have to use regular expressions to extract the subfields from that string. Okay? It works, of course, but it is a hackish idea. The right way to do it, which is harder, is to implement the writable data type that has these two fields or more. Okay, so you have to implement it your own way. So you have to implement a way to read the fields, the data type, and a way to write it. And if that will be an output from the map function, it has to be also comparable. So you have to implement the compare to function. You see here in that part, we are talking about very low-level details, okay? Because now we are talking about Hadoop, not MapReduce, not the concept of MapReduce. We are talking about the actual programming language. Okay? Yes?
Regular expressions, is there implementation on the level of Hadoop for regular expressions? Or
No, because that's customized. That's your way of encoding it. So you have to.
So what I'm saying, when you programming, when you use regex, you use native implementation of regex.
Yeah. It has nothing to do with Hadoop. Yeah, it doesn't. It has nothing to do with Hadoop. I like questions. Where are your questions? Muhammad. I'm not happy. But we'll see the outcome of this, right? Okay. So this is just a summary of the basic cluster components. We have one of each of name node and job tracker. And of course, corresponding to the name node, we have data nodes. And with the job tracker, we have task trackers. So the job tracker is the master node for job submission. So that's the MapReduce part. The name node is the master node for the file system. The task tracker, we have one task tracker per node, which is responsible for processing the task on that node, and the data node also that is responsible of the data that is stored at that node. Again, this is, you saw that previously, right? So that's again combining them together. Okay. Any questions so far? Now let's talk about Hadoop job. So a MapReduce program in Hadoop is called Hadoop job. The job itself will be automatically divided into map and reduce tasks. Each task is assigned to one of the task trackers. Remember here, we have, one of the. So each task will be assigned to one node, either here or here or here. Okay? And you will submit your code to this node. So you will deal with the cluster through just one node. You don't need to log in into any other nodes except the submission node, which you will have access to. So you log in to the submission node, you submit the job, and you don't care about how it will work. Now, an instance of running a task is called a task attempt. Remember, the job will be divided into tasks. Each task will be assigned to a worker or a node. Okay? When it runs, it's called task attempt. It might fail, so we'll have to assign another task attempt, the same task, but another attempt of it, maybe at a different node. Okay, that's why it's called task attempt. Multiple jobs can be composed into a workflow. If you have an application where you see that you want to do some processing first, produce the output, and then this output will be an input to another job, which will be produced and produce another output, that's a pipeline, that's a workflow. Each step here is a separate job. In Hadoop, there is no notion of multiple jobs. I mean, there's no bigger unit than a job. So one job is what we discussed so far. But you, in your application, you can divide your work into pipeline of jobs. But that's your responsibility. Each one of them will be completely separate job, but you will have to run them sequentially. You yourself. So you'll have to keep track of what will be the output of the first one to make it the input for the next one. Sorry, what is the output of the first one to be the input to the second one. So every one of them, you will have to configure it separately. You will have to prepare the configuration object for it and call them sequentially. Okay? Yes?
So if I have two projects, it will be like two pipelines, or it will be...
What do you mean by two projects? Hadoop doesn't know what project means.
Okay, I have two projects to work on it. And what I mean, different tasks.
Completely different.
Yes.
Okay, so that's not a pipeline. That's not a pipeline. You can run them in parallel if you want. Yani, I hope inshallah we'll have time. You will see that all of us will submit jobs almost at the same time, if we would synchronize it. Yeah. All of them will be running on the same cluster, in parallel. That's okay. But that's not what we are talking about here. We are talking about one pipeline of jobs, because they are dependent on each other. Okay? The second one will have to wait for the first one. So you will have to run them sequentially, because the output of the first one will be the input to the second one.
So it will be always one pipeline, or it can be multiple pipelines.
Pipelines here are logical things that you, as a programmer, do. MapReduce doesn't know what we mean by pipeline. Okay? MapReduce will run, the runtime here, will run whatever jobs are submitted. If you have a job that is like that. I don't know why it's this way. Okay. So this is MapReduce 1. This is MapReduce 2. This is MapReduce 3. Okay. This is the initial input. This is the output of the first one would be input to the second one. The output of the second one would be the input to the third one, and then this is the final output. Of course, you should not. Of course, MapReduce doesn't know about this pipeline. You will have to submit them yourself sequentially. So you will submit the first one first. After it completes, then you submit the second one. After it completes, then you submit the third one. Of course, you can encode that into your code. You put the configurations one after the other, and you call the submission one sequentially. Okay, but MapReduce doesn't know these connections. This is a logical connection that you have. Okay, the only thing that MapReduce runtime knows is one job. Submit a job, it will be done. Input and output. What you do with the output, it's your own business. Is that clear now, Ihab? At the same time that you are submitting jobs, others are submitting jobs also to the same cluster. They will be, to MapReduce, these jobs are completely independent. Whether they are running in parallel or in pipeline, they are completely independent because the job is well defined. There is an input and there is an output. That's it. These connections, if you want to connect them, you connect them yourself. Okay? I hope that's clear now. Okay, behind the scenes, there are many things that are done for you. For example, the input splits are computed. You just give the input path, and the input splits are done for you. Remember, what do you mean by input splits? The division of the data into units that will be processed by individual mappers, actually. Okay, not reducers, mappers. Behind the scenes, the job data, which is your jar file and the configuration files, are sent to the job tracker. Once you call the submission function, it will do that for you. The job tracker will put the data in specific location on the machine that will be processed. Okay, and in queue tasks, that's done, and that's hidden from you. Okay, the task trackers will pull for tasks, and the task will start and end without your control, all of the tasks. Okay, and so on. So you are off to the races. Once you submit the job, you will just sit looking at what's going on. You don't need to do anything. You will just track the progress of your job through the web UIs or the terminal that you are submitting through. But once you submit the job, it's done. Muhammad, can you be with me, please? Okay. Okay. Now to a bit more details. The input in the MapReduce job doesn't have to be one input file. It can be one path, but that path has multiple files inside it. Okay? Each input file can of course be can be very big. So it will have to be split into what we call input splits. These are the parts that will be processed by one mapper. Inside this, you will see multiple records here. That's why we have record reader within Hadoop. There is a record reader that will iterate over this split to read the records one by one. What happens when we read one record? This mapper will be, the map function of this mapper will be called with that record. And then we get another record, will be called. And then we get a third record, will be called, and so on. And that will happen in parallel through the different mappers on the, in the cluster. Okay? And each mapper, of course, will write the intermediate output. Now there is just 1 second. There is a type in Hadoop called input format. So the input format defines these two things: how I define the input splits and how I read it. Okay? Yes.
This times, so these columns, is each one in one machine?
What do you mean?
Split. First file.
This part, this is each mapper can run in a separate machine. Of course, they might be on the same machine, but generally they can be in different machines. And if a machine has multiple cores, for example, you can assign multiple mappers at the same time to work on the same machine. Yes?
And if that mapper is get filled, it will switch it immediately to the second mapper, or how it will work?
What do you mean by get filled?
Get filled for any reason.
Failed. Failed. Yes. If that failed, then the job tracker will assign the same task to another mapper. Again.
It will be the same record reader, same input.
Exactly. Yes.
But for that second mapper.
For another mapper. Yes. And that will be done automatically for you. You don't have to worry about that.
So as a conclusion,
As a conclusion, we didn't conclude yet.
Conclusion after this slide.
Yes.
So we have the configuration file. In the configuration file, we are talking
Configuration
about
object.
Object, yes.
Okay, configuration object for the job, because there are configuration files for the cluster itself,
We are talking the path of the files.
of the input.
Of the input. Suppose
Yes.
I have 5 files.
Yes.
Okay. So he will create 4 or 5 inputs. Yes? File 1, file 2, file 3.
Depending on the size of each file, we'll see how many splits for that file. Yes. Yes. You came late, right? We said that one file. I don't remember if you attended that part or not. We said one file is very big, and it is divided into smaller units called blocks. The block is 128 megabyte. This is the thing that is one machine. But one file can, let's say that these are the, I think we'll have a slide like that. We have a slide like that. But one file can have, let's say, 10 blocks. Each block can be on a different machine. Remember, this is on a distributed file system. So one file actually sits on the entire cluster. It's not on one machine only. Okay? Is that clear? Why it's not clear? The input format is the format only. Yes? Yes? Where is your question? Say it again. Yes? The file is a list of blocks. Each block actually will be an input split. Or almost an input split. We don't define the input file, we set the input file, the input path. Can anyone?
This is because she means she has to define the job. The file where it is.
Yeah, when we set the job, we set where the input is. Okay? The input path is just a directory. It can have multiple files.
And
Okay?
Hadoop will do the job for us.
Hadoop will divide these files into logical splits, and each split will be assigned to one mapper.
Based on the size 128 megabyte,
Yes.
And do we have control on this size of the block so we can reduce it or increase it?
Good point. I think when you install the cluster, when you install Hadoop, it is somewhere probably in the configuration files. But of course, once you installed it, you should not change it. By default, it is, I think, 128. But as a programmer, you mean as a programmer? No, you don't have control over the size of the block. It is already defined by the file system. But I'm talking about if you install the file system, I think you have that as a parameter.
I think maybe
Yes.
confusion about input file is just perception that this is distributed file system. It's not single machine.
Yes.
So, I mean, I think that the questions I hear are probably, not taking account that when you say file, it's not one machine.
Yes, we are no longer talking about the regular notion of files. Okay? In fact, as I said, the input file will be partitioned over the cluster. You know what? Each of these partitions, which we call blocks, is actual file on the local file system. It is stored as a file. But the file in the local file system, the standard one, okay? Logically, it is a file at the layer of the distributed file system. Is it clear now? Okay, now we are talking always, MapReduce is talking always about records, key and value pairs, okay? But these correspond to or come from, I think this slide is explaining. These records come from data that is written in HDFS blocks. We say that each block is 128 megabyte. Now, why didn't we align exactly the records with the blocks? Intentionally, we did it that way, that the block actually ends within that record.
for the continuity.
Because when we save the files, we don't know where the file system doesn't know this logical meaning of a record. At the application layer knows that. But when the data is written, it is just chunked at a fixed sizes. When you read it, HDFS doesn't know about what MapReduce is, okay? What the jobs are. So it just exactly divides the data into blocks to be stored, okay? But when you read them back to records, you have to you have to put the records together. So all of these records will come from the same block, which is good, but usually at the boundaries, you might get something from the next block or the previous block. Of course, all of that is done for us. We don't care about that. Okay, but that's what actually is done. Yes.
So you said each block is an input split almost.
Yes, where are the input splits here? Wait. Okay, here are the input splits. The input split, this is the one that is aligned with the records, of course. Okay, because the input split is the input to the mapper. So it has to be aligned with the records, because this is a set of records. But they don't have to be aligned with the blocks. That's why earlier, 5 minutes ago, I said they are not exactly the same. The block and the split, there might be some misalignment. Okay, because the records are the logical meaning of the data, but HDFS doesn't know that meaning. Okay, so this part is 128 megabyte, that's one block. And the split, usually it is also 128 megabyte, almost, doesn't have to be exactly, but it's not aligned exactly with the block. Okay, as you see here. The input splits have to align with the boundaries of the records. That means that this split, when it is assigned to one worker, usually, or the HDFS will try to assign the worker to be on that machine that has that block. Because that's the perfect scenario, right? We don't have to move the data in this case. But we might need some part from other blocks that might come from other machines. It can happen. Yeah, but that would be very small. That would be always a part of one record. Yeah, just one part of one record can be moved from another machine. Okay? I hope this is more clear now. Now, where is the record reader? The record reader reads from that split now. Okay, it will read one record at a time and give it to the mapper. Okay? Now the mapper will produce output records. This output record will go through the partitioner to determine where exactly each record will go, to which reducer. Okay? So you will see here, from one partitioner, you will see one line going to each reducer. Why is that? Yeah, because the output here, some of it might eventually go to that reducer, some will go to that reducer, some will go to that reducer. So usually the shuffling goes from all mappers to all reducers. They have to be, of course, we said that we have to wait until everything is done. Okay? But the transfer of data will go between all mappers and all reducers. Okay? Is this clear? Is this clear why? Okay. Is it clear? No? Okay. What happens in shuffling? We do grouping, right? We do grouping of values that are associated with the same key. Some of these values might be produced by this mapper. And some will be produced by this mapper. And some will be produced by this mapper, right? So eventually this list of values will be processed by one reducer. But to get this list, you have to get the part of it that was produced by that, and the part of it that was produced by that, and so on. So every reducer will read from every mapper. And imagine that I have K, let's say that I have this K, this is the key, and I have V1, V2, V3, V4, V5. Okay? I might see K and V1 here. That might be produced from that mapper. And K and V2 from here, and K and V3 from here, and so on. But all of them eventually will go to that mapper. How will this, will go to this reducer. How will that reducer get all of them? It will have to copy this one from here, and this one from here, and this one from here, and so on. Okay? So the communication will have to happen between every reducer and every mapper. Yes?
Now, in the case of key 1 and V1,
Yes?
it's failed to send key 1 and V1. From where it will get it again?
Okay, you asked the question before, and let me answer it again. Okay.
From replication,
Yes.
for example?
No.
Now I'm talking about the value itself.
This mapper failed before it completes. This is the case, right? Yeah, it produced some records, but it didn't finish. It failed before it finishes its own input split. Okay? That's your question, right? No. Okay.
Maybe I didn't get you. But now the question, I have values, different values, split it into different mappers. Now values...
It's not splitted. It's not split. It was produced by different mappers.
Produced by
Because that's an output. That's not an input. This is an output. That's an intermediate output from that mapper.
Okay. So I'm
Okay.
reading from the data source as an input for the mapper.
Yes.
Okay, so in case if
So
I
that's the input. Input goes here.
so value 1 is coming as input for the mapper.
It's not an input for the mapper. It's an output of the mapper. It's an intermediate output of the mapper. It's not an input. I'm not talking about the input. I'm here talking about the output.
It's data itself, yeah. It's a data itself, yeah. For example, maybe it's word, maybe it's car, maybe anything, yeah.
Yes.
That's the meaning of value here, yeah.
It can be anything.
It can be anything.
Yes.
Okay, now if the mapper failed to process that value 1.
What do you mean by failed in processing? Does it fail completely, or it was not able to process that record?
Only that value. Only that value.
You are talking about input record, right? Not output record.
This is already processed, it's output.
This is output.
Okay, it's filled while it's doing the output. It will take the value 1 again from
Okay.
different input or how to do it.
Okay. There are multiple things here. The mapper can fail to read one input record. Okay? But it can catch that failure and move on and continue. In this case, there is no problem because the problem is in the input source itself. The mapper didn't fail. The failure was in processing one of the input records. That can happen, by the way, and you have to handle it. Your code has to handle it. Okay. Now, what if we didn't handle it in the right way, and that resulted in failure of the mapper task itself? It can happen, right? The mapper now failed, or the machine that is running that mapper failed. It's the same thing. Okay? It failed after it produced some output, some intermediate output. What happens is that the job tracker will know that this failed because of the continuous, and it's not just switch it will restart that task on a different machine. So it will ignore completely the partial output that was produced by that failing node and restart the whole task on a different machine. With the same input assigned to it, of course. Not new input, it will be the same input. Okay? Yes?
Doctor, we talked about the mapper failing, right? So the mapper is assigned different input splits which are stored inside that machine.
Yes. But we are talking about each input split correspond to one mapper. Okay? Okay.
So when this mapper fails, and if you have to reassign this job or this task to another machine,
Yes.
will that machine have the same data, the input splits?
Yes, of course. It's the same task. When I say same task, it means the same input, of course.
No, I mean the data store itself, right? So we said data is stored as replicas.
Yes, it has to get the same split somewhere from the cluster.
So basically, if the mapper fails, it will be assigned to multiple mappers wherever the data was replicated. Is that
Exactly. That's the best way to do it. Exactly. Yes. Because in that case, we don't need even to move data. We will just run it on the machines that have the other replicas. Yes. Yes.
Just to clarify, when you say that each reducer is talking to each number,
Yes.
the output of the mapper.
Generally, of course.
Generally
Yeah.
speaking,
Yeah.
the output of the mapper is dealt with during shuffling. It's grouped, right?
Yes.
So this grouping, does it store the values inside this shuffling?
We'll talk about it. It's coming.
So it's not, I mean, when
It's
saying
coming.
It's not the reducer speaks to the mapper. I mean, obviously the reducer gets the information from shuffling, right?
When it comes, ask me again if you didn't get an answer.
Okay.
Okay?
Second question.
Okay.
Job, you are mentioning job tracker.
Yes.
And in Hadoop 3.0.0, there is no anything called job tracker. There is a source manager in YARN that does the job.
Yeah. Maybe the naming is different.
Yeah.
Yeah. Maybe. I'm not sure. Yeah. Are you sure that there's no job tracker?
YARN is used
For submission of the-
submission
for the
of
management.
And it's called resource manager. When you said job tracker, it took me time to math. That's why
I'm sure that until 2.6 it was like that. Maybe after 3 I will check. I will check and let you know. Yeah. But logically it is the same. Is it more clear or more complex now? Reem, don't care about the quiz, ya Reem. Care about what you learn.
Yeah, we will understand these details once we start doing things. Yeah.
Don't worry about the quiz, please. Okay. إيهاب is smiling طبعا يعني ما عندوش quizzes ولا حاجة فيعني بيضحك. he's watching now the other guys. But you will do the quiz by the way. Okay. طيب, this is from the map side. Okay. Here is from the reduce side. The reduce will produce the output, and they will produce it in records, of course. So there is a class called the record writer who will actually write to the output file. Okay. So you'll have to define also the output format. Remember the sequence files that we mentioned earlier? That is the output format will be. So we have input format, we have output format. There are multiple classes that implement this for you. Okay, so there is text input format, there is key value text input format, there is sequence file input format. So you need to read about that just to get a sense of what the meaning of each, so that when you have your assignments or your project, you don't need to implement these from scratch. There are some of them that are implemented already for you. Myself, personally, I had never needed to implement any of these. I usually use one of the existing ones. But for the data types, I created my own sometimes. Okay. But for the input and the output formats, no, I usually use one of these.
What about CSV files?
CSV files are text files, and they are read by lines automatically. If you define text input format, then every line will be read as a record, right? And you have to parse it, of course. You have within the map function, you have to parse it to get the fields. Okay. Coming. Okay. Here's what happens in shuffling. The mapper writes the output records in a buffer in memory. This buffer is over time is spilled on disk locally. Okay, so the intermediate output is written locally, is not written on the distributed file system. Why is that?
does it spill? Is it spilled by Hadoop or it's spilled by operating system? Does it go to virtual memory or it goes to DFS?
It doesn't go to the DFS. That's exactly what I'm saying.
So what I'm saying, you say spills on the disk. So
Yes,
it spills-
locally.
It spills into virtual memory.
Into disk, whatever disk is defined on this operating system. Okay, we don't.
What
We,
I'm asking, who is doing this? Is it done by
Hadoop.
or by operating system?
no, Hadoop is doing this.
Because if it's operating system, it's virtual memory, obviously.
But Hadoop is talking to the operating system also.
Yeah, but when something is spilling from memory, because memory is getting full, the buffer is
Yes.
spilling on the virtual memory part of the disk.
It's the responsibility of the operating system then to write it to virtual memory or
Or
to,
10 file.
yeah, it's the responsibility of the, but we don't care about these details, okay?
I need to know if there is a method to my madness. So
You can, okay? But at our level here, we don't care much about these very low level details. But it is written to disk anyway locally. This is what we need to know. Okay? Now, these parts of the intermediate output will have to be prepared to go to the reducers. So we have to sort them, okay? And each of these partitions, we have to sort them into partitions by keys. You remember the partition function? The partition function will tell me which reducer this record should go to. So I can have local partitions. Each mapper will have local partitions. Each mapper will have this part of the intermediate output to go to reducer number 1, and this part will go to reducer number 2, and this part will go to reducer number 3. Okay? Now, reducer number 1 has to pull that part from that mapper, and reducer number 2 has to pull that part from that mapper, and so on. That's why we have here other reducers. So that's the first reducer. So this is one reducer, but we have other reducers here. Okay, so the first reducer gets its chunk. So this chunk, this part, is that part. Okay? And this, just one second, and this part that is assigned to the same reducer comes from another mapper. Okay? That's exactly why we said each reducer will get data from almost each mapper. Okay? Yes?
Well, again, I have the same question.
The same question, good.
So, information that is passed to the reducer, is it talk to the mapper, you have one block or one spell waiting for you, or this is the address of your spill, go and fetch it. Why I'm asking? Does the reducer read it from the disk, or it goes to the mapper and says, give me that spell?
What is the difference?
There is a difference, because then it's process the process, right?
I think the reducer pulls the data, so it knows that
So
there is.
it's informed where is the data and it pulls the data. Or it tells the mapper, fetch me the data.
I think the reducer pulls the data from all the mappers.
So this is my question.
But whether it pulls the data or the data is, to us, this
Two
is,
different things.
yes,
You
two
read
different.
The process or you read from the disk.
It's pushing or pulling.
Yes.
Yes, but to us doesn't matter. At our level, it doesn't matter. The data will go from the mapper to the reducer somehow, one way of these two ways. Yes.
Hadoop will handle this.
Of course, yes. Yeah, I have. Hadoop will handle this. Okay? Yes.
Dr. We said the mapper is running on the same machine as the data store to not transfer data.
Not always, by the way. Not always. This is the ideal case. Yes.
So in this ideal case, because we don't have as many reducers, so where is the reducer? Is it on the same machine or?
It can be on the same machine or not, but by the way, it doesn't matter. Why? Because it has to pull data from all the mappers. It's not just one mapper. A reducer cannot be on all machines. It has to be on one machine. Okay? So probably one of the mappers is on the same machine, ya Fatma, or on one machine. That's the best, but the others, of course, might not be. Some of them, by the way, might be, but not all for sure. Because multiple mappers can run on the same machine if the machine has multiple cores, for example. Okay?
One more question. We said each key is associated with a reducer.
Each key is associated, will be partitioned to a, yes, will be assigned to a reducer, yes,
So what
by the partition function.
What happens if this reducer fails?
Same thing when happens when the mapper fails. Again, this task will be assigned to another reducer. Yeah. You didn't answer my question why we why we put this data, the intermediate output, on the local disk, not on HDFS.
For the quick access.
Because the HDFS,
Reading from memory is faster than the
HDFS
We'll spill this to disk locally, not on HDFS. Do we need to put it on HDFS? Putting it in HDFS will make the merging harder, right? And we don't need it, actually. These are temporary files. We don't need to store them in HDFS. Okay? You were saying something.
No, that's what I was saying, that the
Okay.
distributed file system would actually distribute that, which would defeat the purpose of.
Exactly. We don't need to distribute them. Yeah. If you wait for me, you'll get what we want. Okay. The combiners also are running here. The combiner can reduce the amount that we have here if it runs, and also can reduce it before the reducer gets it. Okay? But they are optional. Seeing it in a different way, split goes to one mapper. The mapper produces multiple output records. They will get sorted and partitioned, okay, ready for the reducers to get their own partitions, and the reducers will get the partition. So here we assume that we have two reducers here, right? You look at this, we have only two reducers, so we have only two partitions here. Each partition is for one reducer. So the first one here goes to this one, the second one here goes to this one. From another mapper, again, two partitions. Third mapper, two partitions. Now these partitions at the reducer side will be merged together to produce the input to the actual reducer. Yes.
So here in this scenario, we have only two reducers.
Yes.
So if one of them fails, how will we reassign that?
It's not our job. You mean how technically it's done? Again, as I answered you 5 or 10 minutes ago, if it fails, the runtime will know, the job tracker will know, and will reset the same reduced task to another reducer.
Okay, but we have only two. Or we are using only two. Is that
We are using two, but on the cluster, of course, the cluster is larger than one job. Otherwise, the job will fail because we don't have resources. Okay. Go to your new version of the question. You don't have any questions? Everything is clear? Okay. Okay, one thing that we need also to emphasize is that the output of the reduce function, the reducers will go to HDFS. Not to local files, of course, because we need to replicate it, and that will be kind of preparation if that output will be an input to another job. Okay. Shuffling and sorting in Hadoop, the most complex aspect of MapReduce, but it is done, of course, automatically for us. What happens in the map side? I think this is just an explanation of what we already explained. So the output is buffered, the buffered are spilled, and the spills are merged into partitioned file, and at the reduce side, the map outputs are copied. Didn't say pulled, but I think it's pulled, and merged together. Okay. Okay. Now the workflow. How will you deal with your jobs? Okay. This is you at your convenient room with your convenient laptop or machine. You write your code, which will be the mapper and reducers classes that we discussed. Okay? And Hadoop cluster is somewhere in the cloud. Okay? For us, it will be in QU. which, by the way, in the cloud also. Okay, but it will be accessed through QU. You need to run your job. You need to load first your data into HDFS. MapReduce job takes input from HDFS. So the input of your job has to be on HDFS. It won't be on HDFS automatically for you, right? You have to, you yourself, you have to copy it to HDFS. Okay, so that's the first step. You should of course load the data because data usually is big. Probably you should do it sometime before you develop your data, your code. Okay. And usually the data, because it's really big, it's there. Okay, and you just develop there because you copied at some point in the past, and then you develop your code and you submit your job to the cluster. And then go to step 2 to develop other jobs or modify it or anything, and then you retrieve the output from HDFS. Now, if you want to process the output locally, you'll have to copy it back. But usually the output of Hadoop jobs are really also huge. Okay, so you keep it there, maybe summarize it somehow, do something with it within the cluster, but if you need to deal with it locally, you have to copy it back, but usually we don't do that. Here's how I used to work, okay? I develop code in Eclipse or whatever IDE that you like on local machine. You test on small input samples, so you get you know the data that you will work on eventually is big, okay? But locally, you cannot put that big data on your machine, of course. So you'll have to test on small input samples on your local machine. That's why I told you that you need to install Hadoop on your machine so that you can locally, you can debug your, you develop and debug your code before running it on the cluster, okay? And then you test on a bit larger input samples. Yani you increase the size over time. Don't start with huge files. Okay, start with small portion of the data, very small portion of the data, to make sure that everything is well, data types are defined properly, and then you increase the data a bit. Then once you are confident with your code, then you create a jar file, you copy it into the cluster, and you run that jar file that will submit the job on the cluster. Now, don't start running the job on the cluster on the actual big data at once. I mean, at the beginning. Run it on small input size. So try to have multiple versions of your data, small portions that you will use locally and you will also use on the cluster. Don't start on the cluster. You implemented the program locally and it runs very well on whatever you have locally. Then now run it on the big data on the cluster. Don't do that. Start also running it on small portion on the cluster to make sure that now on the cluster it runs well. Then you increase the size and you iterate, of course. So this is recommended. When you debug, take a deep breath. Okay, start small, start locally. That's what we mentioned in the previous slide, and build incrementally. Okay, don't write big chunk of code and then run it once. Try to build the code incrementally. There are different modes, and I think you should read about that on Hadoop documentation. There is local standalone mode, there is pseudo distributed mode. So local mode means it's just a single node. Pseudo distributed mode, you will simulate that you have multiple nodes, but it's actually physically on the same node, or fully distributed mode, which is the cluster. Okay, so you have to one of these two you will have to do locally. Okay? Usually we do this single standalone mode before you do it on the cluster. Debugging strategies. You know, when I usually teach programming courses, I recommend students not to use print line, although this is the most common way between the students to debug. There are much more efficient debugging ways than writing print line statements. Okay? But for this one, you need to do that. Okay? Because you will not be able to break while you cannot go to the debug mode over the cluster. Okay, and stop the program of running on hundreds of machines at the same time. Okay, you cannot do that. Okay, so you'll have to write a print line statement. But watch out, don't do that excessively, because that will slow your job down a lot. Okay, so don't do that excessively. At least do that for the critical points that you want to test, but don't do it excessively. Okay, that's what I'm saying here. Be careful how much you log. Try to handle exceptions very well. Okay, throw runtime exceptions whenever you might see a problem, or you might expect a problem, and then that way you can debug, and you can know where the problem is, and then you can debug why the problem happened. And capture the state within the runtime exceptions messages. Write down what is the state of your code now, what are the values of the variables, and so on. Okay, programming is still programming. It is programming. Although a new model of programming, now you are programming to run your code on multiple machines, but still programming. Sometimes, as usual, try to be modular. You don't have to put all your code in the map, inside the mapper and the reducer, in the map function and the mappers and reducers. You can, of course, implement some functionalities outside these classes, as usual. Okay, as we do usually, we have multiple. We divide our code into modules, right? Same thing here. We have to have mapper and reducer classes, but they don't have to have all of your code. Do it the way that you used to do. And of course, compose these components within the mappers and reducers.